The circuit I built is supposed to function as a reverse parking sensor, meaning that when connected to power, the red LEDs are supposed to light up one by one as the obstacle moves closer to the sensor. Unfortunately, I was unable to get my circuit to properly work. There were two separate pieces to the circuit that had to be built and then put together. These two pieces are the transmitter and the receiver circuit. Each circuit is meant to have its own 12-volt power supply. The transmitter circuit is composed of a 555 timer, an IR transmitter, and 1 microfarad capacitor, and 3 different resistors. In this section of the reverse sensor circuit, the 10 kiloohm resistor connected at pin 6 and the 1 kiloohm resistor connected at pin 7 are used to reduce the current flow that is inputted into the 555 timer. The power supply is directly connected to pin 4. The voltage that is outputted from pin 2 is then stored in the 1 microfarad capacitor and connected to pin 1, which regulates the frequency of the 555 timer output. The 330 ohm resistor is then connected from power to the IR transmitter in order to protect it from high voltage. The transmitter component is connected to pin 3, which outputs a certain voltage and is then converted in the transmitter into pulses which are to be accepted by the IR receiver. This brings us to the next portion of the reverse sensor circuit, the receiver section. In this circuit, an LM339 IC chip is used as an operational amplifier, which essentially means that it compares two input voltages, and non-inverting and inverting, and then outputs one voltage. The output is considered high when the non-inverting voltage is greater than the inverting voltage, and the output is considered low when the inverting voltage is greater than the non-inverting. This circuit had many components including an IR receiver, 4148 diodes, varying values of electrolytic capacitors, LEDs, and finally resistors. Pin 3 of this circuit was connected directly to power. The non-inverting inputs of the circuit are located at pins 5, 7, 9, and 11. The voltage travels through a 4.7 kiloohm resistor and branches off to pin 7. The voltage then continues to travel through a 1.5 kiloohm resistor and branches off to pin 9. Finally, the voltage goes through a 1 kiloohm resistor and enters pin 11. Pin 5 is connected directly to ground. The inverting inputs are located at pins 4, 6, 8, and 10. The voltage travels from power through a 1 kiloohm resistor. It is then prevented from going to ground through the use of a diode, and travels through another 1 kiloohm resistor, where it splits in two different paths. First, it enters a 100 microfarad capacitor, then travels through a 1 megaohm resistor and a 47 picofarad capacitor, which are connected in parallel, and finally reaches the inverting input pin 4. Going back to where the voltage split into two paths, the second path is where the voltage travels through a diode into pins 6, 8, and 10. The voltage is then outputted through pins 1, 2, 13, and 14. The voltage dissipated at pin 1 is determined based on the comparison between the non-inverting pin 6 and the inverting pin 7. The determined voltage then travels through a 1 kiloohm resistor and used to light the LED if necessary. The output voltage of pin 2 is determined through a comparison of inverting pin 4 and non-inverting pin 5. The voltage then travels in parallel and continues to power the inverting pins 4, 6, 8, and 10, seen here. Pin 12's output is determined through comparison of pins 10 and 11. Its voltage then travels through a 1 kiloohm resistor and based on the determined voltage lights up the second LED. Pin 14's voltage is determined based on comparison between pins 8 and 9. This voltage then follows a similar path to pins 1 and 13 as it goes through a 1 kiloohm resistor and used to light an LED. The IR receiver is connected from pin 4 to ground as it receives the pulses that are sent from the transmitter and converts them into electrical signals.